Have you ever played with a guitar, adjusting its strings to produce different sounds? Imagine that the universe is a guitar, and its strings are the fundamental building blocks of everything we see and experience. This is the essence of string theory, a revolutionary concept in modern physics that aims to unify all the fundamental forces of nature. But what does this theory have to do with astronomy? The answer lies in the cosmic connections between the tiniest particles and the largest structures in the universe. From the subatomic realm to the cosmological scale, string theory offers a new perspective on the mysteries of the universe, challenging our notions of space, time, and reality itself. How can we make sense of dark matter and dark energy? Can we understand the origins of the universe and the nature of black holes? What is the ultimate fate of the cosmos? All of these answers and then some could rest in the fundamentals of string theory, or at least along its roadmap of astronomical physics. In this video, we will delve into the fascinating world of string theory and explore its implications for astronomy and our understanding of the universe. So grab your imaginary guitar, find a quiet, soundproofed room, and get ready to tune in to the strings of the cosmos. String theory is a revolutionary concept in modern physics that aims to unify all the fundamental forces of nature. It's a theoretical framework that proposes that the universe is made up of tiny, vibrating strings rather than particles. The origins of string theory can be traced back to the early 20th century, when physicists were struggling to reconcile two seemingly incompatible theories: Einstein's theory of general relativity, which describes the behavior of gravity on large scales, and quantum mechanics, which explains the behavior of subatomic particles. In the 1960s, a group of physicists working at the California Institute of Technology and other universities began to develop a new theory that would solve these problems. They proposed that the fundamental particles in the universe were not point-like objects, but rather one-dimensional strings, each vibrating at a particular frequency. This new theory, dubbed string theory, would eventually evolve into a much more complex and mathematically sophisticated theory, but the basic idea remained the same, that all particles are made up of strings that vibrate at different frequencies. One of the earliest pioneers of string theory was Gabriele Veneziano, an Italian physicist who was working at CERN, the European Organization for Nuclear Research, in the late 1960s. In 1968, Veneziano published a paper that described a new type of mathematical formula, now known as the Veneziano amplitude, which was able to describe the behavior of subatomic particles called mesons. This was the first hint that string theory might be able to solve the problem of quantum mechanics and general relativity. Over the next few years, other physicists, including Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind, began to explore the implications of Veneziano's work and developed the basic framework for string theory. They realized that in order for the theory to work, the strings would have to exist in a space with more than 3 dimensions, which seems counterintuitive at first, but was necessary to make the math work out. The first major breakthrough in string theory came in 1971, when two physicists, Pierre Raymond and André Neveu, independently discovered a new type of string theory that included fermions, the particles that make up matter. This new theory, called the RNS model, was a major step forward in the development of string theory and provided a framework for building more complex models that could describe the behavior of particles in greater detail. Throughout the 1970s and 1980s, string theory continued to evolve as physicists worked to refine the mathematical models and develop new techniques for solving the equations that described the behavior of strings. In 1984, John Schwartz and Michael Green published a paper that showed the string theory could be used to describe all of the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. This was a major breakthrough and helped to establish string theory as one of the most promising ideas in modern physics. Today, string theory remains a highly active area of research, with hundreds of physicists working to refine the theory and develop new applications for it. While many of the predictions of string theory have yet to be confirmed by experiments, the theory continues to inspire new ideas and challenge our understanding of the universe. The basic idea behind string theory is that everything in the universe is made up of tiny, one-dimensional strings. These strings are incredibly small, and on the order of the estimated length of 10 to the negative 33rd centimeters, and they vibrate at different frequencies, which give particles their various properties, such as mass and charge. In string theory, particles are not fundamental building blocks of matter, but rather they are the different vibrations of these tiny strings. One of the most remarkable things about string theory is that it requires extra dimensions beyond the three spatial dimensions, such as length, width, and height, that we experience in our everyday lives. Specifically, it requires 6 extra dimensions that are curled up into a tiny space known as the Calabi-Yau manifold. This idea might seem strange, but it actually solves a major problem in physics known as the hierarchy problem. The hierarchy problem is the question of why the gravitational force is so much weaker than the other fundamental forces of nature. In our current understanding of physics, gravity is much weaker because it spreads out over all 3 dimensions of space, while the other forces are confined to just 3 dimensions, which makes them much stronger. However, in string theory, the extra dimensions are curled up so tightly that they are effectively invisible at everyday scales, which means that gravity is spread out over many more dimensions than the other forces, making it weaker. This solves the hierarchy problem and provides a possible explanation for why gravity is so weak. The idea of extra dimensions is not new, but it was not until the development of string theory that it became a serious scientific proposal. In fact, the first version of string theory required 26 dimensions, which seemed absurd at the time. However, as the theory evolved, physicists realized they could only compactify the extra dimensions, meaning they could curl them up into a tiny space, which made them invisible at everyday scales. This allowed for a much more realistic theory that could be tested and refined over time. To understand how string theory relates to outer space, it is important to have a basic understanding of the standard model of particle physics. This model describes how particles interact with each other through 3 fundamental forces: the electromagnetic force, the strong nuclear force, and the weak nuclear force. However, it does not account for gravity, which is the force that governs the motion of celestial bodies in the universe. String theory attempts to reconcile gravity with the other fundamental forces of nature by describing particles as tiny, one-dimensional strings that vibrate at different frequencies. These strings have different energy levels that correspond to the different types of particles in the universe. By unifying gravity with the other fundamental forces of nature, string theory offers a new perspective on the nature of the universe. One of the areas where string theory has important implications is in the study of black holes. Black holes are objects in space with such strong gravitational fields, not even light can escape them. According to string theory, black holes are not just objects with mass, but also objects with a certain amount of charge related to their vibrations. This charge is known as black hole entropy and is directly related to the number of different string states that can be used to describe the black hole. Another area where string theory has important implications is in the study of cosmology, the study of the origin and evolution of the universe as a whole. String theory predicts the existence of extra dimensions beyond the 4 dimensions of space and time that we experience in everyday life. These extra dimensions are believed to be curled up into tiny compact spaces, and that are not directly observable. However, Their existence can have important implications for the nature of the early universe, such as the origin of cosmic inflation and the nature of dark matter. While string theory offers a new perspective on the nature of the universe, it is currently a purely theoretical framework that is yet to be directly tested. However, there are ways in which the details of the universe can either prove or disprove string theory. For example, the Large Hadron Collider, the world's largest particle accelerator, may be able to detect the existence of extra dimensions predicted by string theory. In addition, observations of the cosmic microwave background radiation may prove evidence for the existence of cosmic strings, another prediction of string theory. Cosmic strings are like a giant spiderweb spanning the entire universe. This cosmic web is made up of cosmic strings, long and thin stretches of matter that are predicted by string theory. These strings are like cracks in the fabric of space-time, remnants from the early universe when it underwent a rapid expansion known as cosmic inflation. Overall, string theory is a theoretical framework that seeks to unify the fundamental forces of nature, including gravity, by describing particles as tiny, one-dimensional strings that vibrate at different frequencies. This new perspective of the universe has profound implications for astronomy, black holes, and cosmology. While string theory is currently a purely theoretical framework, there are ways in which details of the universe can either prove or disprove its predictions. It makes the melodies of string theory an exciting area of research heading into the future, for scientists, astronomers, and other members of the band of researchers alike.